In this video, we're going to be describing how we can use matrices and their organizational techniques to assist us in solving these systems of equations. So the first thing we're going to do here is introduce what is known as the three elementary row operations. The three elementary row operations are operations that can be done to a matrix without impacting okay, there we go, impacting the solution of the system. So the matrices that you get after applying elementary row operations are said to be row equivalent to one another. So two matrices are row equivalent if elementary row operations have turned one matrix into another. So I start with a matrix, I apply some elementary row operations, I wind up with a second matrix. The second matrix is row equivalent to the first matrix. So the three elementary row operations are permute or swap two rows, the notation that I like to use for permuting two rows is I specify what two rows they are, and I use this notation for it. This notation says that the ith row will become the jth row, and the jth row will become the ith row. The use of the arrow says it will become this. Next up, we can multiply a row by a non-zero constant. And somehow that statement seemed to have turned Google Assistant on. That's enough out of you, cell phone. We'll use that constant times the appropriate row will become that row. Good. And then finally, here's where the elimination addition comes from. You can add a multiple of one row to another row. This is where we would say something like C times the ith row. We're going to add that to the jth row, and that will become the new jth row. Now some comments on this. Here are some things to not do. Don't take multiples of both rows and have it become the jth row. Don't do that. That is no longer row equivalent to what we had previously. Break it down into two separate steps where you're taking the second constant times that row and then adding. Another thing to not do, and this is in the same vein, but don't subtract them. This does not produce something that is row equivalent. It's got to be specifically we're adding a multiple of one row to another row. Now, this may seem insignificant for the time being, but it does have a very specific purpose later on in the course, and I will call back to this at that point in time. Now, with that in mind, we use these elementary row operations in an attempt to get a matrix into what we refer to as row echelon form, or REF for short. A matrix is said to be in row echelon form if all of the following are true. Any rows comprised of entirely zeros are at the bottom the matrix. The rows of zeros are at the bottom of the matrix. Next up, the first non-zero entry of every row is a 1. And that 1 is referred to as a lead 1 or a leading 1. Let's gussy up these ones a little bit, make them look pretty. The lead 1 or a leading 1. Next up, every entry below a lead 1 is 0. Every entry below a lead 1 is 0. Now, there is one last one that is sort of implied by this one, but, in fact, let me draw you a picture. Let's say in the first row, you have your first lead 1, then that means you'll have a bunch of zeros that are below it. That means that in the next row, that lead 1 will have to be to the right of the lead 1 that is above it. And we get this sort of staircase pattern with the lead 1s. So the lead 1 in lower rows must be to the right of lead 1s above it. And we get what's called the staircase pattern. That staircase pattern is crucial to what we're doing. The act of obtaining row echelon form is referred to as Gaussian elimination. Gaussian elimination. There we go. Now, just like Taylor had a McLaurin, Gauss had somebody who came along and said, you know what, I want to make this process even easier, and I want to talk about what's known as reduced row echelon form, or RREF. So this guy by the name of Jordan if you're a generic English speaker like I am, Jordan came along and said, you know, this every entry below a lead 1 is great, but why don't we change that to below and above? So this is going to be the same as row echelon form, except that in number 3, it's going to be every entry below and above a lead 1 is 0. Every entry below and above a lead 1 is 0. Now, it still lends itself to a staircase pattern, but the staircase pattern will be both above and below those ones. Now, Jordan was kind enough to allow Gauss's name to be first, but this is now referred to as Gauss-Jordan row reduction. The process of obtaining reduced row echelon form is Gauss-Jordan row reduction. In the next videos, we'll see several examples of obtaining row echelon and reduced row echelon form.